Okay, this is logs day 9. Base E. What is E again? Do you remember? About 2.7, and then if you're going to go further, 2.718. 2.718. It is a number, and it turns out to be this amazing thing in calculus. And I don't want to spoil it for them, but E is the only thing that does some special stuff in calculus. Okay, it's like really, it's really a cool number. And so basically, the E, the exponential number, is this 1 over 0 factorial. Wait a minute. Isn't 1 over 0 supposed to be, like, illegal? Therefore, 0 factorial must mean something different than 0. Well, 0 factorial is defined as being 1. That little exclamation mark means factorial. Do you know what, like, 4 factorial means? Do you have any clue? Yes?
4 times all of it.
Yep. 4 times 3 times 2 times 1. Yep. So if you had 3 factorial, it'd just be 3 times 2 times 1. It's times all the numbers in front of it. That's correct. Okay. So E is equal to 1 over, and again, this is really defined as 0 factorial is defined as 1. And so 1 factorial means 1 times 1, which is 1. So this is 1 over 1 plus 1 over 1, which is really like 2, right? Plus 1 over 2 times 1, which would be like 1/2. So with these first 3 numbers, I've gotten it up to 2.5. 1 for this, 1 for this, 1/2 for that. 2.5 plus, and again, it ends up being 2.718, blah, blah, blah. But all these numbers that are like unique, like pi and like E, they are nested fractions. They're like a whole bunch of fractions added up forever. And this is, again, something that you learn how to do in calculus. You learn how to do these adding up a series or a sequence. This is called a series. Adding up a series of numbers that go on to infinity. So in other words, you just keep going with that pattern forever. That's why this number keeps going forever. And it never repeats, and etc. All right. So here is something that you totally won't understand until you get to calculus. Even my pre-calculus students probably not have a clue how to do that one. E is the limit as x approaches infinity of 1 plus 1 over n to the power of n. We have had exponentials, so at least you could have a clue what that would mean. And it basically means you just keep on adding them up, and you keep on putting in another number. Like, let's say n is 2, then you make it 1 plus 1/2 squared, and then you make it, you could make it 3, and then this would be to the third. All right. So there's a couple ways you can calculate E, but basically, if you can just remember it's about 2.718, you're good. So do you get that log base 2.718 is really close to log base 3? I mean, 2.718 is really close to a 3, isn't it? Okay, so it's pretty much just log base 3, just a little less. So what do these look like? When you actually graph it then, would you agree that log base E is about the same as log base 3, which log base 3 just went something like that. So it just looks like all the other logs. Okay, but this is the ultimate one, where if you take the exponential, which is y equals e to the x, and you graph it, it goes like this, as compared to the other one, the red one here, which would be the log base e, and that's like this, log base e of x. And those two are inverses of each other. And this, again, is something that you will learn more in pre-calculus. You'll get into what does an inverse mean. It means the x's and y's have been reversed. So like, for instance, right here, instead of 1, 0, it's 0, 1. All right, so the x's and y's get flip-flopped. All right, so there's a lot of reasons why this is really cool, and I've given you a few here. But if all you can remember is that log base E means about log base 3, it's really close to log base 3, then that's fine. That's good enough for now. You don't really have to, like, explain exactly how to determine E or anything like that. You just have to know E's about 3. That and that are the same thing, okay? ln and log base E. This is probably the number one thing that you have to be able to do today is whenever you see an ln, that stands for log natural, you got to replace that with a log base E. Because here's how the problems will look now. ln 6 equals 10. And then they say, well, maybe you should rewrite it to get your answer. But it doesn't have a base. But it does have a base. Because if you do what I said, rewrite ln as log base E, now it's got a base. So now you could say it's what to the what equals what? E to the 10th equals, let's say that's B. Sorry, I should make that a better letter. Like a B. All right, so equals B. Now, e to the 10th is about 3, 2.718. So 3 to the 10th would be a huge number. So B is a really, really, really big number in this problem. But the point is you wouldn't have been able to rewrite it like this unless you knew to rewrite the ln as a log base E. And I encourage you to always do that. All right, so see how this teacher's doing the same thing? Best tip of the day, whenever you see an ln, rewrite it as this, log base E. Okay, so we're going to make a quick sketch of all of these. Log base 2. That is a really rough sketch, too rough in fact. But if we want to make it, do you agree that we all have to go through this point? And do you agree that it always has an asymptote that runs right down the y-axis like that? Okay, so sketch it with me, please. Then for log base 2, I'm just going to do a quick rewrite. I'm not going to really think this too heavily, but 2 to the y equals x. So then if I put in like x is, or no, let's put in a y. Let's put in y is 1. Then this is going to be x is 2. So 2 comma 1. Could I put in another one? Could I put in y equals 3? Yeah, y equals 3 would give me 2, would be 8. 8 comma 3. There's a few points. Now I got a much more accurate graph. Okay? Now it's log base 3. Generally, they take a sharper turn. But it always goes through this. And it always gets closer and closer to the y-axis. So then let me just try to do this without having to like rewrite this thing. What if I put in x was 3? Would that work nice? Put in x equals 3? Yeah, what do I get? 1. So then the difference here is it went 3 to the right and up 1 versus this one went 2 to the right and up 1. So it took a sharper turn. And the next one that would be logical would be 9, if x equals 9, because then you could know the answer was 2. Because it's like 9 becomes 3 squared, so it's 2. Goes through there and there. All right, so it's just a little sharper turn, that's all. Wait a minute, this one has no base. So what's the base? 10, very good. Most of you knew that. So then that means if I put in x is 10 right here, x is 10, y will be 1. That's like the sharpest turn of them all. It has to go through this spot. And it has to get closer and closer to the y-axis here. So super sharp turn for log x. That's called common log because it's the most common one used, which is why the calculator defaults to base 10. Okay. Base 25, this is madness. Still has to go through this spot right here. Now it's just going to be like way over here, super sharp turn, almost not even rising, just incredibly sharp turn. All right, log base E, again, has to go through here, has to have an asymptote right here. I guess I didn't do that on this last one. There we go. And that's about like log base 3. Do you get that it's almost identical because base E is 2.7 and base 3 is a 3, and so they're pretty much the same thing. It's 2.7 instead of 3. I bet you can't even tell the difference on the graph. Okay. And then ln x, wait a minute. What's ln? Natural log, which means log base E, so it's the identical thing to this. So you can just go like, yeah, that's the same graph. All right, so this is just meant to remind you that log base E just looks like all the others. It's just a base that's close to 3, pretty darn close to this one. These two are almost identical. All right, so natural logarithms are just logarithms with a specific base. Again, this is not a variable, it's a number. Okay, so then I know the answer to this one already. I can just look at it and go, oh, I know the answer. Because why? Because if I rewrite the ln as a what? Log base E, then it's log base E of E to the 15. And now do you see the answer? If these two are the same, do you remember this deal? Then the answer is 15. Okay. So how about this guy? Well, that means E to the power of log base E. Notice all I'm doing is rewriting ln's as log base E's. And if these two are the same, what's the answer? 2. Remember that from this? If I had 5 log base 5 of 12, the answer was 12. If these two numbers were the same. See, it's like this is a base, and that's a base. The base of the log versus the base of an exponential. Then, if the bases are the same, that's the answer. Okay, moving on. Find the ln button on your calculator. If you haven't already got your calculator, I'll get it out now. The ln button is underneath the log button. And it says check the examples from the last page, which are these right here. Ln of E to the, oh, wait a minute. Yeah, these are they the same? I hope they're the same. Yeah, they are. So they've already rewritten them for you here. And you can just hit ln button instead of log base E. You type in ln, and then you still have to put in an E. In case you don't know, the E key is above the divide. So ln E power of 15 and the parentheses, because the order of this thing really matters a lot. ln key, then the E key, then, nope, we'll probably need, oh, it starts with it has an automatic parenthesis will be like pop up as soon as you say ln. E, and then caret 15, and the 15 is actually 2 keys, and then end parenthesis key, and then equals, or enter. Okay. What'd you get? 15, just like we expected. Okay, this other one, E to the power of ln2. Try it. We know the answer is supposed to be 2. Just make sure you know how to type it in right. Because if it doesn't come up to 2, it only means you didn't know how to type it in right. Okay. Now this brings up an interesting point. Log base 3 of 17 is the little problem they give you now. Log base 3 of 17. If you do log 17 over log 3, do you remember that that gives you the answer if you want to, get the answer on the calculator? Okay. We told you that that changes it to base 10. What we didn't tell you, because you didn't need to know, was that you can change it to any base you want by doing that same thing. Because log base 10 of 17 is the exact same thing as log base, now I should clarify, This whole thing would be the exact same thing as if I changed it to base 9. It could be base 9, could be base 13, it could be base 75. It doesn't matter. Isn't this kind of weird? If you want to use base 9s, go ahead. It'll come out the same. Now, you don't have a base 9 button on your calculator, do you? But you do have a base E on your calculator, and I just told you that you can change it to any base you want. Therefore, shouldn't you be able to do ln 17 over ln 3? That just means you change to a base E, right? If you do it this way, or you do it this way, you will get the same thing. Because when you do a change of base, you can change it to any base you want. You can use base E, therefore, the ln button works just fine. Now, just to clarify, am I saying that you will get the same thing if you type in ln 5 or log 5? No, you get different things. It's just that when you divide them like this, the base 10 numbers are smaller, but they're both smaller. So when you divide them, you get the same thing. The log base E, the ln's, the log base e's, those numbers are both a little bigger. But when you divide them, you get the same thing. So that leads us to, if I said, rewrite that as a base 74. You could. Really easy. Just tell me what you think that is as a base 74 problem. Yep, you got it. This is super simple. Don't type anything on your calculator. Yep, that's what I was looking for. Yep, that's what I was looking for. We just did base 10 before? Yep, because it was the one your calculator could do. Yep. So now, I just go log 12 over log 9, but that would be in base 10, and it can be in anything. So I asked you to use base 74, so log base 74. Log base 74. All right, moving on. Here's an application question. One of the things that's cool about E, this is just one of the things, but is that you can do a special kind of compounding that the banks actually use in the real world. They use what's called continuous compounding, which means that they use an E in their formula for compounding your money at the bank. I think most of you guys probably have a bank account, and you're probably earning some small, incredibly small, amount of interest, and then that's compounding, not just daily, not just by the minute, but continuously. And the way you do that is by using E. So, here's the problem. $5,000 is invested at 9% interest, compounded continuously. How long will it take to double your money? Recall the continuously compounded interest formula. A equals P E to the RT. That's E is just a number. It's 2.718 though, so don't think of that as a variable. It's not. P is a variable though. It's the principal, the amount that you put in. The 5,000 goes there. It says double your money. That's going to make it 10,000, right? And where does that go? In the A. And then the rate, do we know the rate? Look. Oh, 9%. And then what don't we know? The time. So we leave T alone. And then we have to solve for T. All right, so if you stick these numbers in with me, we're going to have 10,000 equals 5,000. E, which is a number, 2.718, to the R, which was what? 9%, so 0.09 T. This is a typical question that you would have on the test. That's an application question involving E. So all I did was stick numbers in a formula. That should be your happy place. You by now, but for as algebra students, if they give you the formula, you just have to stick something in. That's life is good. That's easy. Okay, now you got to get the clump alone. That's the clump. You have to get it alone. So what do? Divide by 5,000. If you think about that, this makes this nice and easy. What's 10,000 divided by 5,000? 2. 2 equals e to the 0.09 t. Whatever shall I do? I've got an x in the exponent. It's an exponential. The only thing that fixes exponentials is what? What haven't we done yet on this problem? And the whole unit's about this. Logs. So now, if we have an x in the exponent, that's how you fix that, is with a log. So can I rewrite this? Yeah. I go log base, take a wild guess, e. Log base e, also known as ln, but I'm going to say log base e of, and then you jump around, 2 equals, jump back, 0.09 t. I'm getting into some complicated math here. It's awesome. You started with a formula. You had to know how to stick the numbers in the formula. Then you had to know how to get the clump alone. Then you had to know how to rewrite it as a log. You had to bring logs into the problem. And now, how do you finish the deal? Well, you'd need a calculator, because nobody in here has probably memorized log base e of 2. Okay? So you use your calculator for that. And how do you do log base e? With button. Yep, ln, the one right above, or right below log. The ln button, ln2, and then you get a decimal, and then it equals 0.09 t, and then how do I get t alone? You divide by 0.09. What was that decimal for? 693, is that it? Is it go? 47, okay, we should probably put in as much as we can. Remember, you don't want to round until the very, very end. So put in as many decimals as you can stomach typing in. Again, in the smart way to do it is your calculator's already got all the decimals in there, right? And you do that second answer thing. Because now you take this and then you keep that answer in there and you just say divide by 0.09. What's the final answer? 7.702? And then I want you to think for a second, in the context of reality now, is this like how many toenails are in the waste paper basket? No. What's it about? It's about time. What's it about time for what? It's in years. It's the years that it took to double your money at 9%. Is investment. And so just to make sure you understand what you're getting at the end, what you have. What you have is how long will it take to double your money? 7.7 years. That's the thing that people sometimes don't think about. You know how doubling makes a number grow really fast, right? 2, 4, 8, 16, 32, 64, 128. Okay, so what if that was in thousands? You had 2,000, and then it's 4,000, then 8,000, then 16,000. And then it starts to grow pretty fast at the end, 32,000 to 64,000, and 64,000 to 128,000. What if those were in millions? And that's one of the reasons that wealthy families and wealthy people get wealthier, is because they can make their money grow like that. And if your family has had a lot of money for a long time, think about this. If you're the Gates family, they already have a ridiculous amount of money. And over the next however many years, if it doubles, like every 10 years or so, 7 years in this example, then if money's going to double every 7 years and you're already a gazillionaire, isn't that insane how it just goes up, 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 up? All right, and that's one of the reasons they say the rich get richer. Well, there's a reason for that. It's because of compounding. Now, of course, if somebody's really rich and then they just spend it all, then it doesn't compound. It just goes away instantly. So there are people who sometimes They have a lot of money because they make a lot of money, but they spend it all every year. And then at the end, they really don't get to do this at all because they had a high income, but it doesn't grow at all because it just stays the same because they always spend it away. All right. Population of Spearsville, Mrs. Spear made this one, I'm guessing, is growing at the rate of 3.5% per year. Assuming it keeps going that way, if 20,000 people live there in 2012, how many people will there be in the year 2020? I don't have a nice, easy way to do this one until, oh, there it is. They give you the formula. Now, all I have to do is figure out what to put where. It says P0 is the initial population. It's kind of like, U sub 0 being like the beginning. Okay, so the initial population goes here. And that's the 20,000. So the 20,000 goes right here. And it looks like we need to solve for, do we solve for T or do we solve for P? Which one do they give us, T or P? They give us T. They give us the time. Because they say 2012 and 2020, how many years? That's 8 years later. 8 goes in there. Now you just got a formula that you have to solve for P, which, P is already alone over there. So it's going to be easy. P equals 20,000 times E, which is a number, 2.718, to the 0.035 times the T, which is 8. So that's something your calculator can handle. Just take the equation, stick the numbers in. All right, you have learned now everything you need for the logs test. The logs test is not tomorrow. We get a data review tomorrow. And then on Monday, you take your logs test. It is not this Friday. You are correct. On the notes it said Friday. I double checked even that day and made sure that, I thought it was even during your hour, I made sure that it was not Friday, it's Monday. But anyway, it's Monday, for sure. Okay, so the tests this Friday, and today's assignment's worksheet 9. Why do mathematicians like national parks? Because of the natural logs. That's pretty bad. I do have a special place in my heart for the national parks. I've always been in fact, when I was a little kid, I wanted to be a park ranger. That's what I wanted to do. I was going to be a ranger all the way until I was like, I don't know, freshman in high school or something. Then I started to think about it more and be like, but I'd have to live in the middle of nowhere. Like, maybe, I just wasn't really up for living in the middle of nowhere. Maybe some people, that sounds awesome. But, okay. Then I went and tried a school. I tried doing a little practice teaching at a school, and I really enjoyed it. And then I'm like, you know what? I think I'm going to go for teaching. And then I was like, okay, if I want to teach something, what should I teach? And my best subject was always math. I always liked math, so it was pretty logical after that. Okay, that's all I got for you for today.